P.7 Complex Numbers. So let me talk first about what a complex number is. And again, kind of like when I talked about complex fractions, complex does not mean complicated. It's just the name they came up with. And it uses another name, imaginary, which also does not mean does not exist. Okay? Imaginary does not mean like your imaginary friend. It's not the imaginary we're talking about. Complex numbers are numbers that have the form a plus bi. A and b are real numbers, and I is a number called the imaginary number or the imaginary unit. I is equivalent to the square root of -1. Or another equal definition is to say that I squared is equal to a -1. Imaginary units are actually really easy to work with. I hope you will find that this section is very smooth and very quick to do because they are really easy to work with. They're almost like working with a variable, okay? Now, the catch on that is this idea that when you see I, you do need to remember it actually has a value, and its value is square root -1. Our first two questions here are to decide if the number given is a real number or an imaginary number, and then to write it in complex form, a plus bi. So what do you think? -72. Is it a real number or an imaginary number? It's a real number. What do you think? -I square root 5. It's imaginary. To write it in a plus bi form means to identify which piece is the real part and which piece is being multiplied by the imaginary unit. So we already said in number 1 that the number -72 is a real number, so it's the a, -72, plus 0i, because there is no imaginary unit in that particular problem. So it's just 0i. So that's fine. 0i is 0. But that's how we would write it in that form. On the second one, there's no real component, right? There is no number being added, so that's our 0. And then it's negative. And we write the number part first, so that's the square root 5 part, and the I second. Please be careful that the I does not creep underneath the radical. It's not under the radical. It's outside of it. Okay? Be careful when you're entering at my math lab. Make sure that it doesn't accidentally get sort of grouped underneath there. It'll kick it back out at you and tell you you're wrong. Okay? The I is not under the radical. Simplifying, which is where we're starting, or where we're going next, with imaginary units, it's really easy. Simplifying looks a lot like working with variables. We combine like terms. So -3 plus 2i plus 5 minus 6i. The real parts, -3 and 5, can be combined to give me a 2. The imaginary parts, for 2i and -6i, can be combined to give me a -4i. Easy, right? Yeah. Subtraction's the same way. We just have to be careful to distribute the negative. So I have -3 and +4i. And I combine like terms. The real parts, 6 and 3, combine to give me, it's 6 and -3, sorry, a 3. And the imaginary parts, -7i and +4i, combine to give me -3i. Combining like terms. Simple. Multiplication and division are also very similar. There is a catch on them that makes it look a little different. So let's start with multiplication. Multiplication, we're going to FOIL, just like we did with binomials, right? First terms, 3 times 5 is 15. Outside terms, 3 times -2i would be -6i. Inside terms, -i times 5 would give me -5i. And the last terms, -i times -2i would give me +2i squared. And here's the catch. I squared is equal to -1. So we have to change that. This 2 needs to be multiplied by -1. It will become -2 at the end. The pieces before it also can be combined, right? -6i and -5i would be negative 11i. And it also means then that this 15 and this negative 2 can be combined. So I have 13 minus 11i. I know I'm moving fast. I apologize for that. But if you need to go back and rewatch the video to catch the pieces, you can do that too. Yes, ma'am?
Does it have to be written like that?
It does if you're writing it in the a plus bi form. If you wrote it the other way, it would still be correct unless the directions specifically told you write your answer in a plus bi form, and then it might kick it back at you and say, you didn't do it right. So, okay, here's the deal with division. We've seen what we're about to do once before. We saw it when we used radicals. Do you remember when we were using radicals and denominators and we heard this phrase that said something like rationalize? And we used something to rationalize called the conjugate. That's exactly what we're going to do for these. This is just what we've done before, but we're doing it with i's instead of radicals. So what would the conjugate be for 1 plus 4i? 1 minus 4i. You got it. And if I multiply that on the denominator, I do it on the numerator as well. And we choose to multiply the denominator by that because it is a difference of squares. That's why we did it. So my denominator is 1 minus 16i squared, which is 1 plus 16. Now let me finish the numerator out because I haven't multiplied it yet. Remember, there's distribution in my numerator. First term, 2 times 1 would be 2. Outside 2 times negative 4i is negative 8i. Inside negative 3i times 1, negative 3i. And last terms, negative 3i minus 4i would be positive 12i squared. Change all those I squareds to negative 1 and then you're almost done. I have 2, I have 8, 9, 10, 11, negative 11i, and then minus 12 because it's I squared, right? So the positive 12 becomes a negative 12. And on the bottom, this becomes 1 plus 16. So 2 minus 12 is negative 10 minus 11i, denominator 17. Here's a really good way of addressing the last question that you had. Remind me your name? April. Okay. April asked, how do I need to, does it have to be written that way? This answer is completely, totally simplified. It's a perfectly valid answer, right? But it's not written as a plus bi. So there's a very good chance that if the directions say write your answer as a plus bi, that it's not going to accept this as your answer. It's going to want you to do this. Because that's a plus bi form. All I'm doing is separating each piece of the numerator and writing it individually over the denominator. There's nothing special about that. It's just in the form that's considered the standard form for complex numbers. All right, so we've established that I squared is negative 1, but what happens when we have i's that are bigger exponents, to higher powers? How will those simplify? Well, let me go through with you and notice that there's actually a pattern in how the relationship is determined. So take a look. I to the 1 is just I, and I squared we said is negative 1. If we were to take I cubed and break it apart into I times I squared, recognizing and remembering that I squared is negative 1, this would simplify to negative I. And if we were to break apart I to the 4th into I squared times I squared, which would become negative 1 times negative 1, right? We would see very quickly that we get the number 1. So I to the 4th is a very unique way of rewriting powers as just the number 1. So when we get to I to the 5th, it's super easy to think I to the 4th times I, and I to the 4th is 1, so this is just I. Okay, got those all boxed in. I to the 6th, again, would be I to the 4th, and then I squared. Well, I to the 4th is 1, I squared is negative 1, And hopefully you see we've got a pattern established. We went from I to -1 to -I to 1. I to -1. And if we went I to the 7th, it would be -I. And I to the 8th would be 1. So what we're going to do when we look at these is we're going to look for ways to break these apart into I to the 4ths. So in particular, and I'll show you how to do it in maybe a visual way, and then how to do it in a simplified thinking too. I to the 19th, well, I can write I to the 4th, and another I to the 4th, that's 8 of them. I to the 4th, that's 12, and I to the 4th, that's 16. And that leaves me with I to the 3rd. All of these I to the 4ths are 1. And we know that I to the 3rd, based on what we just wrote down, is -I. So this value is -I. But there's got to be a way. I mean, like, I don't know about you, but 77, writing that out as 4, 4, 4 all these times till I get up to 77, that does not sound like a fun experience to me. So it is an easier way to do this. What we can actually do is we can take the number 19 and we can figure out what happens, when I divide it by 4. Now, if you did it long style, like back in elementary school, and you wrote it maybe instead like this, you would find that you would get 4, and that would be your 16, and you'd have a remainder of 3, right? The remainder of 3 tells you you're going to have an I cubed left over. Well, that's useful because you know what I cubed is. It's -I. And all of these that came out evenly would be able to be written as I to the 4th, I to the 4th a whole bunch of times. So in all reality, it's the remainder that tells us which of the 4 portions of this, sequencing I, -I1, or I, -1, -I, or 1 that we're in. But it's even better than that. Because you see, when you divide these, think again now like with your calculator. Put in your calculator 19 divided by 4. It's going to give you 4.75. And I don't know how much you sort of think or reflect upon how that 0.75 works, but that 0.75, of course, is related to the remainder. A 0.75 is equivalent to a remainder of 3, right? Because it's 3/4. If I had gotten something with a 0.5, that's equivalent to a remainder of 2, because it's 2/4. And if I were to get a 0.25, that's equivalent to a remainder of 1. And a remainder of 1 tells you you're back at the I to the 1, equivalent to a fraction of 1/4. And then if you have a whole number, right, there's no decimal point, there's no remainder, that actually tells you that you have a remainder of 0, i.e., this is something that's just a bunch of I to the 4ths. So it's the 0.25, the 0.5, the 0.75, or the whole number that actually allows you to figure out, at a glance, which of the sequence this is in. So let's give it a try. I'd like for you to take 77 and then divide by 4. 77 divided by 4 is 19.25. Whoops. 19.25. 0.25 means that I have a remainder of 1. And a remainder of 1 tells me that this can be broken apart into something where I have I to the 1, and the rest of it I to the 76, right? The rest of those pieces are equivalent to the number 1. So all I'm left with when I have a remainder of 1 is I to the power 1, or I. The number 9 is a little bit different. We've got a negative exponent. The negative exponents aren't too bad. You guys know how to change negative exponents into positive exponents. We simply write them as a denominator. So this would be 1 over I to the 5th. Well, I to the 5th is 1 over I to the 4th times I, or just I, right? We've already done that one today. So this is 1 over I. But we're going to leave our answers with rational denominators. So we're going to rationalize by multiplying by I. So it'll give me I over I squared, and I squared, of course, is -1. So the net result ends up being a negative I. This is just some fun with powers. They're easily manipulated, easy to work with, as long as you recognize the patterns. All right, so we kind of jumped in the middle of what I is going on and doing, but we didn't actually sort of start at where I starts. I actually comes, of course, from having negatives underneath radicals. So in particular, if you had something that wasn't a -1, but it was negative something else, there has to be a way to separate those, and in fact, there is. So we're going to talk about roots of negative numbers. If b is greater than 0, then the square root of -b is equal to I square root of b. And the reason that happens is because we had a property of radicals in an earlier section that talked about the fact that if you had the square root of -b, which is the same thing as the square root of -1 times b, this would be the square root of -1 and the square root of b. And of course the square root of -1 is I. So that's actually where that's coming from. So we end up with this as our expression for how this works. Now, there is a disclaimer, a warning if you will, here at the end that says get the I out first. We do. We have to deal with the i's, with the negative parts, before we deal with combining or simplifying anything else. Now, on this one, number 10, we can do it at the same time, it's no big deal. The negative gives me an I, and the 16 square rooted is a 4. The negative on the square root 25 gives me an I, and the 25 gives me a 5. So this is 4i plus 5i, which is 9i. That's wonderful because, of course, the radicals were actually able to be simplified, but they aren't always. Sometimes we still have numbers left underneath the radical, and that's going to happen in number 11. So we have the square root of -6 times the square root of 2 minus the square root of -3. This is a really good example of a place where we do need to be very careful that we make sure that we get the negatives out from under the radicals first. So this is I, and then unfortunately I can't simplify square root of 6, it's just square root of 6. And then I have square root of 2 minus, and then I give an I and a square root of 3. So that's the first step. Get the i's involved, get the negatives out from under the radicals. Our next step then is to distribute. So I have I, and then I have square root of 6 times 2, because they're both underneath the radical. They'll both stay underneath the radical with multiplication. That always works with multiplication. Don't do that with addition and subtraction, it's not appropriate, but it works with multiplication. The next piece, I have -I times I, so there's -I squared, we'll have to deal with that in a minute. And I have the square root of 6 times 3. Okay, so as you know, 6 is 2 times 3. So if I've got two 2's, I should be able to pull one out, so this is 2i radical 3. I already dealt with mentioned that I was going to have to deal with the fact that that I squared is -1. So this is minus a -1, and we're going to put a plus 1 here in a minute. And again, the 6 is 2 times 3, so I've got two 3's underneath the radical, so the 3 can come out with the square root 2 still underneath. So I have 2i square root of 3 plus 3 square roots of 2. Now again, just like we have talked about before with the a plus bi, a is written first. A is the part that doesn't have an I with it, so that's 3 square roots of 2, plus, and then it should be bi. Well, the part of this that's not I is the 2 and the square root of 3. And then the I is written outside of the radical after the square root of 3. And that would be our final answer for that one. One last question. One last question might be, well, but where do these negatives underneath radicals actually come from? Where do we see them happening? When will I be able to use this to do anything with it? And that's a really good question. So this attempts to answer at least where we'll see them showing up from a practical sense of solving a particular kind of problem. We'll see them show up when we're solving some quadratic equations. And so here's an example. If you'll remember, the quadratic equation is -b plus or minus the square root of b squared minus 4ac over 2a. I'm just going to do the plus one here because it's enough to show you where it's coming from and to get the point across. I've got values given to me for a, b, and c. b is -4, so this is the opposite of -4, plus the same -4 squared minus 4 times a, which is 5, times c, which is 1. And it's all written over 2 times a, which is 5. Obviously at the beginning, opposite of negative 4 is positive 4, plus negative 4 squared would be negative 4 times negative 4, or 16, minus 4 times 5 would be negative 20, all over 10. All right, and then 16 minus 20 is negative 4, so there's that negative underneath the radical, over 10. So the square root of negative 4 would be 2i. So an answer to this, if we're not worrying too much about simplifying further, would be 4 plus 2i over 10. You should notice pretty quickly that everything's divisible by 2, so at the very least that simplifying by 2 should happen. 4 divided by 2 is 2, 2 divided by 2 is 1, 10 divided by 2 is 5. So a simplified version in fractional form would be 2 plus I over 5. But notice, that's actually not in a plus bi form. So if we're looking for a plus bi form, it'd be 2 over 5 plus 1 over 5 times I.